All right, so this is team ranking 1. So here I want to sort of lay out the situation and see how this turns into a mathematical problem. So here's the idea. Is we have a bunch of teams that play a bunch of games, and each team has a numerical outcome. So one team beats the other team by some certain number of points. So suppose some teams play games. They could tie as well. In each game, one team beats another by some number of points. Could be 0. So then the question we want to ask is, after all this happens, how can we rank the teams? So specifically, how can we, we'll say rank, or even assign a ranking, like a numerical value? How can we rank these teams? So let's look at an easy example. Suppose, for example, we have 3 teams. Team 1 beats Team 2. In this example, we'll have 3. And Team 2 beats, sorry, I'm struggling with my words today, beats Team 2. Team 2 beats Team 3. And let's say Team 1 also beats Team 3. So clearly, this is really easy. We would say that, well, Team 1 is better than Team 2 and Team 3, and Team 2 is better than Team 3, so we might suggest this kind of order. But what if we had the following situation? Suppose Team 1 beats Team 2, Team 2 beats Team 3, but then Team 3 beats Team 1. Now I haven't done anything with numerical scores just yet. I'm just looking overall. So now it's not so obvious. Right? Maybe it depends upon the scores. You know, if the score differences for some of these games are bigger than the score difference between other games, that might be a thing, right? So let's see how this can give us a system. So suppose we have a number of teams and they each have a ranking number. So suppose we assign the rank. These could be integers or real numbers. They could be positive, they could be negative. So we assign rank R sub I to team I. And if teams will say I and J, suppose they play a game. Where team I wins by, say, P points. So we might suggest the following. That the ranking of team I minus the ranking of team J, if I wins by P points, we might say it's that the rankings should be P points different, for example. Right? Now, if they lose, we could have P less than 0, or just reverse it. Doesn't really matter. And if there's a tie, we can have it equal to 0. So everything's sort of taken care of here. Right? So look at an example. Suppose we have 4 teams. They play 6 games. So team 1 beats team 2, say, by 2. We'll say team 1 again beats team 2 by 1. They play 2 games maybe. We'll say team 1 beats team 4 by -2. We can count that as a loss. I could have written this as team 4 beats team 1, but doesn't matter. I'm going to put them in sort of decreasing numerical order here. So say team 2 beats team 3 by 1, team 2 beat team 4 by 3, and last but not least, team 3 beat team 4 by -3, so it's a loss. So if we write this as a system of equations, this is what we get. So we get R1 minus R2 is 2. We get R1 minus R2 is 1. We get R1 minus R4 is -2. We get R2 minus R3 is 1. R2 minus R4 is 3. And R3 minus R4 is -3. Now, this we can write as a matrix equation. So what's nice about this matrix equation is each column is particularly nice, or rather each row is particularly nice. It has a 1, a -1, and a 0 and a 0. So like the first two correspond to the first two games. And then, so that's why we see the 1 and the -1 for team 1 and team 2. And so on. Then we have a ranking vector, R1, R2, R3, R4. Then we have all the scores on the right-hand side. 2, -1, -2, 1, 3, -3. Now, we can immediately see, for what it's worth, that this has no solutions. Now, in some cases it might, of course. In our case, it doesn't because of this. Right? We cannot have both of those things true. So no solutions here. Right? So we might say, well, maybe we try least squares. So I'm going to sort of flip to a new number here and say least squares. And so this is what happens, right? We'll try it. Right? So what I'll do to make things neat and tidy is I'll call this A, call this R hat, and we'll call this guy B. So if we calculate with least squares, we calculate this. Sorry, this should be a regular R up here. R hat is what happens after we do least squares. So now we have a hat. So I won't show this calculation. I'll just show you the end result. But if we do this, this is what we get. We get this new matrix, which we want to pay close attention to. There are a bunch of things you may notice about this. Like the matrix is symmetric, things like this. We're going to run through all of this. So notice I have stopped here, right? I haven't gone on and just multiplied both sides by the inverse. The reason is that this doesn't work. And so what I want to do now is take a look at some properties of this matrix. And the vector on the right-hand side. So just for reference, I'm going to call this matrix M. I'm going to call this vector over here Q bar, just so we can talk about them. So here are a bunch of things to notice. And in the book, I worked these out in more detail. Some of these are pretty obvious. Some of them I worked out in more detail. Here, I'm just going to illustrate with our example, but not go too crazy. So first of all, notice that M is T by T, where T is the number of teams. So like in our example, so I'm going to make these comments in general about M, but I'm going to refer to this specific example to help give us support. So like in this example, it's 4 by 4. Now, second thing is a little more interesting, a little more subtle, so we need to look at an example. So the diagonal entry M, say I, this is the number of games team I played. Total. So we can see this, for example, if you look at, say, team 1. Team 1 played 3 games. Right? That's reflected in this 3 right here. And the same will be true for the 4. The 4 is the number of games team 2 played, and so on. All right, so that one's pretty easy to see. Now, when those are different, this is the negative number of games teams I and J played against each other. So, for example, if we look in our matrix, we could say, for example, team 1 played team 2 twice. First and second game. That's reflected both here and here. This is why this is symmetric, because team I and team J versus team J and team I, same difference, doesn't matter. So we can say, of course, that M is symmetric. Which is sort of handy. Now, there are last couple of comments I want to make. Let me, I don't want to erase too much. Let me erase a little bit of the screen, and then we can make our final few comments. So next bullet point is to look at the vector Q. There are 2 more things I need to say about M, but I'm going to need to erase some spaces. Let me say the one thing I need to say about Q first. So the ith entry of Q is the total points earned by team Q. So, or team I, rather. So to look at an example of that, we could, for example, say, like if we look at team 1, right? Team 1 earned 2 points here, and 1 point here, and negative 2 points here, total amongst all its games. So team 1 overall, team number 1 overall won a single point, and that's reflected right here. Now, let me do this. Let me clear the bottom of the screen, and then I'll fill in some comments about M, but we don't need these team scores anymore. All right, a few more observations. So first, if you look at M, if you notice, each row adds to 0. Each column adds to 0. Now, those are equivalent because it's symmetric. The reason for that is the following, is that in a sports team sense, is each row / column contains the information about that team. So I'm going to say row / column because it's symmetric. Either one is true, so I'm going to say row / column a lot. Right? So this contains the info on that team. So, for example, row 1 or column 1 is about team 1, etc. Now, here's the thing: if you delete the information about one team, just one team, you can figure that out from all the other teams, because if you know how they did, then you know how they did with respect to that missing team's information, and you can figure those out, right? So we can say this. So team-wise, if one team's row is deleted, or row / column, we can recover it. Now, more specifically, if you look at the matrix, each row or column is the negative of the sum of the other rows or column. So specifically, in M, each row / column is the negative sum of the other rows / columns. So what this means is that the rows are not linearly independent, or the columns. This is why we stopped here, is the matrix won't have one solution. Right, it will have infinitely many. Now, keep in mind, it has at least one because it's a least squares problem, which means it either has 1 or infinity. If the rows and the columns are not linearly independent, then the matrix is non-invertible. The determinant is 0, and it will have multiple solutions, in this case, many, many solutions. Now, here's the fun part. that leads us to a solution that will sort of fix least squares or make least squares work here is if we delete 2 rows or columns, that's like what happens in a team sense is we lose all the information between those 2 teams. For example, if we deleted rows 3 and 4, we don't know what happened between teams 3 and 4. That information is not contained anywhere. So what that means is if we remove 2 rows, the resulting matrix, or if we remove 1 row, the resulting matrix is linearly independent. Right? So we'll say this: if we remove 1 row or column, the resulting rows columns are linearly dependent or independent, because removing yet another this is a bit confusing, but we'll say means we can't get that row back from those others, from the, let's say, those that remain. Now, what this means in a practical sense is that suppose we do the following. If we remove one of these rows or columns, if we can put in a row or column that's linearly independent from all the other ones, then we'll get a nice matrix. Let me sort of clear the screen and sort of talk about fixing the problem, and then we'll fix the problem with this matrix, and then we'll have a nice solution. So let's say for fixing. Remember, so the problem here, just so we know what we're fixing, the problem is this matrix M is not invertible, so we cannot solve for R uniquely, and we'd like to get a nice unique ranking. So this is the deal, right? We will replace 1 row. We could do a column, right? And you could do any column or any row, but sort of standard operating procedure is to replace a single row and a single specific row. We'll replace 1 row with a new row, which will be linearly independent from the others. So in this case, the resulting matrix, the new matrix, will be invertible. Right? So what we'll do is we'll replace the final row by all 1s, and we'll also replace. Now you may wonder why 1s, right? And that's fine, right? So I'm going to clarify this with our example. So we'll also replace the final entry in Q by 0. So back to our example, right? So this is what we get. This is what we had. So we had, I'll just rewrite this. So what we'll do is we'll replace this. We'll replace the final row. Right? And so the thing to keep in mind is, if the technical detail is a bit confusing, which is understandable sometimes, is that the final row depends upon all the other rows, because the final row is basically the negative sum of all the other rows. So which means I can throw that final row out, and I haven't really lost any information. So what I'm going to replace it by is this. 1, 1, 1, 1. And this by 0. So you might wonder, like, what the heck just happened, right? You're like, well, what did this do? So think about what that says in terms of the scores. Well, here's the deal. If r hat is our ranking vector, what this is saying is we're going to assume, we're going to force the sum of the 4 entries, right? If we think about this pink calculation, when we apply it to R, what this does is this forces the sum of the entries in R hat to be 0. Now, this may seem a bit weird, but it's actually fairly reasonable because what it does is it sort of centers the total scores. Around 0. It has no impact on the comparison between them, right? So it doesn't change the order. So in our example, this new matrix, this one, right? This new matrix equation has a single solution. Or least square solution, or if you like, modified least square solution. This is 19/26. This is 9/26. These are exact, and then I'll give approximate. So the approximations are nice because they give us sort of numbers we can sink our teeth into. So it's 731.346 negative 1.577 and 0.5. So what we would say in this case is these are the numbers we assign to the various teams. So we would say this is team 1's rank, this is team 2's rank, so team 3's, this is team 4. So if we wanted to sort of give them a greater than or equal to comparison, we would say that team 1 is on top. It's slightly better than team 4, which is slightly better than team 2, which is significantly better than team 3. Team 3 did really, really poorly. Now those scores add to 1. That's a result of the pink calculation. Doesn't really matter that they add to 1, right? If they added to 5. Right? So something to keep in mind here. Actually, a couple notes I want to make is the 0 right here on the left is somewhat arbitrary, right? You could have had these scores add to 5 or 10 or 1,000,000 or 6.3. It doesn't change the ranking between them. Now, one last thing that I should have made clear when I said about adding these ones in. This new row that we've added is linearly independent from the other rows because when you dot product it with the other rows, we always get 0. So this row of 1s is perpendicular to each other row because the dot product is 0. So it's linearly independent. And it's sort of a side note. It's an important side note, but it's a side note. So this is generally how the method works out. Now, what I'll do is let me pause there. In the next video, I'll summarize the method because in practice, there's a lot of this calculation that doesn't need to be done in the sense that we can go to the final matrix equation fairly easily. But this is sort of like sloppily, in a sense, laying out the method, seeing why we make the changes that we make, and so on.